Okay, hi everyone. In this video, we're going to go ahead and talk about how to predict the products of different types of reactions. And we're going to kind of simplify things and just focus on two reactions in this video, combustion reactions and double replacement reactions. So for chemists, it's really important to know what is produced by a reaction. This way we can be sure that we're doing safe things. We don't get something unwanted as a product that is either difficult to dispose of or something that's dangerous to us. So it's really important to kind of know what we're doing before we do it. So that's where predicting products comes in. And like I said, we're going to simplify things quite a bit, and we're going to focus on just two types of reactions, combustion reactions and double replacement reactions, which will include acid-base since they're a subcategory. First off, for combustion reactions. The good news here is these are the easiest reactions to predict the products of because we always get the same two products, carbon dioxide and water. Guaranteed, that's what you get for combustion reactions. It's also really easy because you have the same two, or mostly same two reactants. So you have some kind of a hydrocarbon, and this will be given to you. You get told the formula is something like C3H8 for propane, or methane, the example we'll do is CH4. So I will give you the hydrocarbon. All that you need to do is add the oxygen to it, and then go ahead and write the same two products, CO2 and H2O. Now, you should be comfortable with balancing these hopefully by now. Remember, balance carbon first, hydrogen second, and oxygen last. And that is a key last step for predicting product reactions. So let's go ahead and work through an example. Okay, so let's go ahead and work through some examples. The first one tells us that methane, and it gives you the formula is CH4, burns in air. So this is a key hint that you have a combustion reaction. Anytime it talks about burning, a flame, combust, those are all signs that you have a combustion reaction. So this is actually giving us a hint on what the reactants are, because air specifically is made up of oxygen plus some other stuff. But as a reminder, combustion reactions always have a hydrocarbon plus oxygen, okay? And then they always have the same two products. So we get carbon dioxide and water, H2O. Now we are also told to write a balanced equation. So we have our equation written out as a skeleton, but now we need to go ahead and add the coefficients to balance it. So as a reminder, with combustion reactions, we want to balance the carbon first, hydrogen second, and then the oxygen last. So if I go ahead and do my atom inventory, I have 1 carbon, 4 hydrogen, and 2 oxygen. And on my product side, I have 1 carbon, 2 hydrogen, and 3 oxygen. So my carbons are already balanced. I'm going to skip right to my hydrogens. I'm going to put a 2 in front of my water, which changes the number of my hydrogens and the number of my oxygens. And then to finish balancing it up, I'm going to put a 2 in front of my O2 to give me the 4 oxygen. Okay, so the other type of reaction that we need to predict products for are double replacement reactions. Now, these are a little more complicated than combustion reactions, but they're still pretty straightforward because you will always be given the cations and the anions for the reaction. And all that you need to remember is that they're trading partners. Don't forget, though, cations will still be with an anion, okay? We don't have two cations together. So with this, the key thing is you need to be comfortable with writing ionic compound formulas. If you're a little rusty on that, make sure to look back in your notes on chemical bonding and ionic compounds to get some extra practice with that. Otherwise, a few quick reminders. When we crisscross the superscripts to get the subscripts, remember we just take the numbers from the charts. We do not use the plus and minus sign. Those just disappear. In the boxes, if we can reduce them, we want to go ahead and reduce them to the smallest whole numbers possible. And then finally, if we have polyatomic ions and we have a number in the box after it that's greater than 1, meaning we have more than 1 polyatomic ion, we need to add parentheses around it. So let's go ahead and try out a few examples of this. Okay, so let's go ahead and try this next example. So this is going to be a double replacement reaction, and specifically it's an acid-base reaction. The way I know that is I have hydrogen and I have hydroxide. So Double replacement reactions are just a more generic term for acid-base reactions, or acid-base are just a more specific type of double replacement rather. So I'm going to combine those two things. Remember, we need to trade partners. So HOH is going to become my water, my H2O. And then I'm going to combine my two other things. So my sodium and my fluorine. So remember, we write the metal first, the non-metal second, and then we write their charges. If we flip-flop them, okay, we get sodium with the 1 and fluorine with a 1. 1s we don't need to write, so we're just going to go ahead and write out that formula, which is NaF. Okay, so if we look, this is already balanced. We have a total of 2 hydrogen, 1 oxygen, 1 sodium, and 1 fluorine. So that is our balanced acid-base reaction. And then finally, let's try one other example. So here I have iron chloride and barium hydroxide. So the iron is now going to be with my hydroxide, and the barium afterwards is going to be with my chlorine. Remember, they trade places. So write the metal first and the non-metal second. In this case, it's the polyatomic iron hydroxide. We know hydroxide is always -1. For our iron, we need to look back at the formula since it's transition metal. It could be different. In this case, it's going to be +3. Okay. So I'm going to take my numbers and go ahead and crisscross them. And if you need help figuring out that charge of the hydroxide, make sure you look back on your ionic compound notes. Okay, so since we have a 3 in the box, that applies to my polyatomic ions, we need to add parentheses. So that's going to be FeOH3 plus the other thing I have. I'm going to have my barium. And barium is always +2, and chlorine, which is always -1. So if I go ahead and flip-flop those numbers, not the charges, I end up with BaCl2. So that gives me my skeletal equation, but I still need to think about balancing it. Okay. So in particular, if I look at my chlorines, I have 2 on one side, 3 on the other. Since I have to use whole numbers, I need to find the least common multiple. So we're going to get up to 6. So I'm going to put a 2 in front of my iron and a 3 in front of my barium. And then we just basically do the reverse. So here I have 3 hydroxide and I have 2 hydroxide. So now I put a 3 in front of my barium and a 2 in front of my iron to balance that out. So I hope that helps. If you have any questions, please let me know. Bye.